Hello, everyone. Welcome to SEM-Israel Virtual Technology Week. I am Andrew Farrugia from Agile Analog, and today I'll be telling you all about analog IP and our new approach that uses design automation. So at Agile Analog, we're changing the world of analog IP. And I wanted to start off with a brief introduction to analog and analog IP. So analog is a key part of any silicon chip. So it's the interface to the real world. And the real world is analog, so it's continuous values of information, but our computers only handle digital data, right? So we need a way to interface one to the other. So over here on the right, you can see a typical SoC, where you have a microprocessor or DSP or GPU, which is all digital, together with some digital control logic and some memory. Then you also have a number of analog components, and these are the main classifications of analog and analog IP, right? So you have power management. This is required to connect the chip to their power source, to adapt voltage supplies to the requirements of the circuits on the chip. You have clocks and timing. This could be anything from generating the clock for the microprocessor to generating the signal for an RF synthesizer. Then we also have measurement. So if you want to measure anything or drive anything in the external world, you need some form of data converter. This could be an ADC or a DAC. And finally, you have communications. And communications could be wired interfaces, such as Ethernet or even SerDes. And they could also be wireless or RF interfaces, such as Bluetooth, Wi-Fi, cellular, you name it, right? So like a lot of other stuff, analog needs to be redesigned for every new silicon process node or even for a silicon variant. However, the vast majority of analog IP is currently hand implemented. And this makes it slow, expensive, and variable in quality, which leads us to the challenge which is facing the industry. So the demand for analog is increasing significantly. SoCs are becoming more complex with higher levels of integration, including RF. Most chips now have advanced power modes, even if they're plugged into a socket, and they will need integrated power management units or PMUs. At the same time, with the advent of home automation, industrial IoT, IoT in general, and the number of new applications, the number of real-world interfaces is increasing drastically. Now, at the same time as the demand increasing, the number of silicon process variants is also increasing. So we're not just talking here about stuff at the leading edge, so 3-5 nanometer designs, but even if you go back to, let's say, more traditional planar nodes, we're seeing a number of new process technologies like FD-SOI coming out, and even for traditional processes, we're seeing the foundries targeting or retargeting different variants of a single process to different applications. So I think on 28 nanometers, there's now 8 or 9 different variants. Some are for low power, some for high performance, et cetera, et cetera. Now, analog IP is generally only available on a subset of processes, and this is because of the traditional business model for IP, which is build once and sell many. So each new process requires analog to be ported, and this is costly and often generates suboptimal solutions. So this cost of porting results in a one-size-fits-all IP being available. So IP providers want to make one IP and sell it to as many customers as possible, and even then only on the most popular processes. This means you could end up with many excess features which you might not need for your application, and these features cost power and or area, right? And even worse, we've had cases where customers have avoided picking the best process technology for their application simply because they could not find the IP that they needed on that process. And as a general rule, the quality of customized deliverables is poor. And this is primarily because they're manually generated. And this translates into a reduced reliability on the long run for the final product. Excuse me. So at Agile Analog, we're solving all these issues. We're delivering high quality, optimized analog components on any process quickly. And the way we do it is using design automation. So we have our own in-house tool, which we've called ADS, or Analog Design System. And this tool has 4 components as inputs to it. So you have the customer requirements, so the exact specifications for that particular block in that application. A design recipe, which is generated by our analog designers, and is valid for a particular type of block. You have the process data, so you can change PDK if you want. And it sits on top of current EDA solutions. So we're not trying to reinvent the wheel in terms of simulators and other tools. So these 4 components go into our ADS design system. The wheel turns and we output a set of automatically generated deliverables. And these include the traditional deliverables that you would expect. So GDS, CDL, LF, and timing models. But on top of that, we also provide a range of other deliverables, including a number of different types of models, reports, integration guides, and test guides, which I'll go into a bit more later on. Now, before we go into a bit more detail, I wanted to review with you why analog design methodologies haven't changed over a number of years and the sorts of problems that we're trying to and managing to solve with our tool, right? And the reason is that analog design is different, right? Especially if you compare it to digital design. Analog design is reliant on the transistor physics of a device. It's a transistor level design approach. It's sensitive to PDK in idiosyncrasies or model changes. It is highly process sensitive, which makes it less deterministic across multiple nodes. That's more on the fundamentals, so on the device physics sort of level. But once you get, even when you get up to the actual design and the way things are designed, you have a number of factors which complicate issues further. So interstage dependence, these are impedance levels and voltage levels, feedback loops. You're very sensitive to the system level, and system designs can change throughout the design cycle, changing the requirements on the analog and sometimes even resetting the design to the beginning. You have a number of complex trade-offs that you're trying to deal with when you're designing any analog block. And all these factors mean that it is inherently an iterative design process, right? It also means that it's hard to abstract. And on top of that, because you want to optimize for each application, almost every single design is different, right? Now, why hasn't this solved before? So to solve these issues, you need to have a technologically and commercially viable solution. And these are the factors that we've addressed within our tool, right? We have something which is scalable from simple to complex designs. It's capable of dealing with different types of designs and different levels of specifications. It's flexible, so we deliver the exact specifications, not just a modular subset of the specs. We can support complex analog requirements, including multiple feedback loops. You need to be able to recreate across different PDKs without additional work and without requiring specialized foundry support, right? You want to leverage existing EDA solutions. You want to take advantage of the past 50 years of innovation that has been going on in the EDA industry. And on top of that, you also want to build on the best practices that designers have garnered through experience and trial and error over the past 50 years. You want to put that knowledge into your tool to be able to deliver better and higher quality results. And from a commercial perspective, you also the tool needs to be scalable, so you need to be able to allow many simultaneous customer projects on many different nodes. And this is what we've incorporated into our tool. And this leads to a number of benefits, both to the IP and obviously to the customer and the customer's product, right? With our approach, our IP is redesigned from scratch for each customer. And this means that you get the exact specifications, not the closest one available off the shelf. It also means that you're optimized in terms of power, performance, and area. The design methodology itself, because it's automated, it's programmatic, systematic, and repeatable. And this, in the end, translates into IP, which is more verifiable, more robust, and more reliable, right? The comprehensive documentation, which is automatically generated as well, allows integration to be easier, and it also takes the products to production, right? And finally, it's lower risk, right? We use proven architectures, which are verified by analog designers, and the quality of the deliverables inherently makes it more reliable. Let's look at our deliverables. So we come from, our team at Agile Analog comes from an SoC background. We've all had IP delivered to us or delivered our IP into other people. There's both internal IP and external IP. Our team has previously taken a number of complex chips into mass production and sold in high volume. So we know how to make a complex SoC, and we know what it takes from an IP set of deliverables to enable an easy integration and functionality, right? So the automatic generation process means that all our deliverables are generated from a single source, which is the customer specification, right? This means that you do not have errors which could show up at integration, which are typical errors that you would see from a manual process where pin names not matching or even pin directions not corresponding on different views. Now, these sorts of problems tend to show up at integration, which is the later stages of the design cycle where people are under time pressure and delivery is on a critical path. Simple mistakes like that could lead to delays, and they can be extremely costly, right? Our deliverables, because they're generated automatically, are guaranteed to be high quality and consistent. On top of the traditional views, we provide an integration guide, which helps to facilitate the integration, also test guide. We also include a tape-out checklist, which is basically a summary of all the knowledge that we as a team have garnered over the years of taping out chips to make sure that basic mistakes that tend to happen do not happen, right? Going beyond tape-out, we provide support into mass production. So we measure our success by our customer success, and that means that is when the product is in mass production. So overall, our deliverables package reduces integration time, and it minimizes costs and increases reliability of the products. So as a quick summary of Agile Analog, what we do is we enable you and your teams with the ability to get analog IP, which is of the function and configuration that you want, so not the closest version available off the shelf, on the technology node that is most suited to your application and with the latest PDK, and we do this quickly. On top of that, you have multiple axes of freedom on how to use your IP. You could use it as a single instance or as multiple instances in your design. You could use it on multiple designs and multiple configurations, and you can even use it across multiple process nodes or flavors, right? Finally, we provide full support from specification through to design, integration, and on into mass production. So now I want to focus on an example to illustrate the sort of problems that you might see. So this is a SAR ADC. And here you can see 6 different types of applications that require different types of optimization, right? So starting off on the top left, you have automotive. Here you have a wider temperature requirement and increased reliability. If you go for a wearable, then you're usually area critical and you want ultra low power. If it's a secure application, you want high precision and absolute accuracy. If you're doing, for example, a portable medical device like a thermometer, then you need low power and high sensitivity. For wireless transmission, you generally need high bandwidth and high accuracy. And if you've got a home device, then you want low area. And if you're doing audio processing, you'd want something like multi-channel. So you can see that just one type of product could be optimized in multiple dimensions. And this is the beauty of our tool, right? So we can start off with a single product, and through using our design system, we can produce IP that is optimized for different applications and generally on different processes as well. So all these applications would typically be on different types of processes to optimize the performance of the overall system. So let's look at our first ADC product. So this is more or less a general purpose ADC. Key features include a 12-bit resolution, up to 20 megasamples per second, multiple input channels, rail-to-rail input, buffered or unbuffered. You could have a differential version or a single-ended version. Performance-wise, you have low INL and DNL, a higher dynamic range. It includes a programmable reference voltage and has lower power consumption. This product is available on CMOS and FD-SOI processes down to 22 nanometers, and FinFET support will be coming shortly. So let's look at an example implementation that we generated using ADS. This was initially designed on 22 nanometers, and then we regenerated it using ADS on 28 nanometers. So this block has 2 types of parameters, what we call input parameters. So these are your typical ADC specifications, so sample rate, bandwidth, a number of channels, linearity, ENOB. And then you also have what we call the control parameters. These are sort of the general operating conditions. So things like temperature range, the process technology and the process options, your supply, any margins that you need on the actual input parameters, and even physical specifications such as the aspect ratio. What we taped this out on 28 nanometers. This was targeted at an IoT application. It was a 10-bit 5 megasample per second version of the ADC. It included 8 input channels with selectable input buffers, integrated band gap for reference and bias current generation. It also includes embedded digital block with integrated level translators. And to facilitate integration and control from the digital end of the SoC, we also have an APP bus, right? And here on the right, you can see the architecture together with the typical parameters that we had for this ADC. Quick overview of our other analog IP products. So we have our ADC, we have a DAC, supply regulators, voltage and current references, a temperature sensor, our C clock, body bias generator for FD-SOI, and a programmable comparator for interrupt generation, supply monitoring, and other applications. So quick summary, so Agile Analog, we're changing the face of analog IP. We provide a repeatable, scalable, high quality approach to designing analog IP, which fits into the current ecosystem. The IP is configurable to the customer's needs with a high quality. It's available when the customer needs it and on the process that you need it. So we encourage you to ask us questions and come and visit our booth after the presentation. Thank you very much, and I hope you have a great show.